So, question one, part A. Um, the idea here is we're trying to think about which of these reactions is more spontaneous or more non-spontaneous, as it were. So, when you're asked about something like this, what I'm hoping that you look at are really two big things, right? Chemically speaking, if one side of the reaction has more resonance, that means that side of the reaction is more stable. In reaction one, the carboxylate has resonance and the aldehyde doesn't. So reaction one seems to be less stable from that perspective. Reaction two, more stable from that perspective. Reaction two, the reactants have resonance, the products have less resonance, so less spontaneous. In addition, reaction two goes from two things to one thing, entropically unfavorable. Reaction one, water is solvent, right? All the stuff happens in the water, so we really don't think about water impacting entropy a lot. So here we're going from one thing to one thing in reaction one, and in reaction two we're going from two things to one thing. So reaction two seems to be more non-spontaneous because both an entropic argument and a chemical argument based on resonance. When I look at reactions and try to predict spontaneity, those are the two things you can always look for. You may not always be able to get useful things from it, but those are things you can look for. Okay? So if reaction two is non-spontaneous, if this overall reaction is spontaneous, then yeah, reaction one has to drive it. Moving on to part C. If we're told the reduction potential of NAD+, which is the cofactor involved in reaction one, is negative, that means reducing it is not spontaneous, right? Remember, delta G is equal to minus NFE naught. So a negative reduction potential means a positive delta G contribution. So under these conditions, under standard conditions, reducing NADH or reducing NAD+ won't help make that spontaneous. So the oxidation of the aldehyde has to be incredibly exergonic for this reaction to overall be spontaneous, and it really is. Okay, part D, thinking about the phosphoryl transfer potential. Just what you're really looking at is the proximity of charges, right? So the hydrolysis reaction for ATP is the same as the hydrolysis reaction for 1,3-BPG, but 1,3-BPG has two phosphates in really close proximity, and that's going to be really destabilizing. In addition, you have this mixed anhydrides, right? So you have a phosphate coupled to a carboxylic acid. That's going to be highly likely to be hydrolyzed. Okay, and then going on to question number two, the keto. So if you don't remember keto-enol tautomerizations, this is the chemical reason why the other high energy phosphate compound of glycolysis has a high phosphoryl transfer potential, right? Phosphoenol pyruvate, which we see in the picture in the bottom right corner, is the enol tautomer. When we hydrolyze it and remove that phosphate, the massive driving force is the conversion of that enol tautomer to the keto tautomer, and that's incredibly spontaneous. So the two high energy phosphate compounds we're going to see in glycolysis, those that are able to phosphorylate ADP and produce ATP at the substrate level, these are those two compounds. And understanding why they're able to phosphorylate ADP is going to be beneficial. Okay, any questions about that? All right, so then question number three, soon here, we're going to, what I would encourage you to do is just kind of follow along and draw things in as we go, okay? Because over the next about 20 minutes of class, we're going to go through the steps of glycolysis, and you should be comfortable filling these in. All right, so here's the overall process, okay? Back in the day when I used to really like playing with Adobe Illustrator, I made this thing. These days I don't want to spend that much time making all this stuff anymore. But so the idea here is it kind of maps out the overall process. This overall process, we see 10 enzyme catalyzed steps. If you go through them, you're going to want to be comfortable naming all of them. Name the enzymes. Okay. There are 9 metabolic intermediates. If there's 10 steps, there's a starting point, an ending point, and 9 things in the middle. You're going to want to know what these things are. Okay? There are 2 high energy phosphate compounds. You just saw them in your activity. The high energy phosphate compounds, you can always predict where they are based on where the ATP gets produced. Okay? So in our payoff phase, we see ATP gets produced once we make 1,3-BPG, 1,3-bisphosphoglycerate. ATP is made in the next step. That means 1,3-bisphosphoglycerate is a high energy phosphate compound. And when we say that word, when we say that term, high energy phosphate compound, we mean something able to phosphorylate ADP, something capable of creating ATP at the substrate level. Okay? So 1,3-BPG is one of them, and the other one is phospholynyl pyruvate, the very last step. Okay? 1,3-BPG and PEP are, I would contend, the 2 most important intermediates in glycolysis because they are the 2 high energy phosphate compounds that are able to create ATP. In a little bit here, when we think about the chemical logic of glycolysis, we're going to see that so much of it boils down to making steps that otherwise might not be logical unless the goal was to create a high energy phosphate compound, right? The goal of these steps is going to be to create a high energy phosphate compound. All right, glycolysis is composed of 3 irreversible reactions. The rest of them, under the conditions of a cell, they tend to be at equilibrium. There's only 3 of them that are irreversible, only 3 of them that are highly exergonic. And in the context of metabolism, when we say irreversible, that's what we mean. We mean highly exergonic, very spontaneous. Okay, everything else is reversible because it's at equilibrium under standard cellular conditions. There are 2 carbon atoms that are oxidized, and we can predict this based on the step that involves a redox cofactor, right? In this step where we convert glyceraldehyde 3-phosphate, GAP, into 1,3-BPG, here we see that we are reducing NAD plus to NADH, okay? Which means something gets oxidized, and that something is carbon 1 of GAP. I have an aldehyde, I end up with basically a carboxylic acid, right? This reaction is what we saw in question 1 of your activity. Okay, 2 carbons, and the reason it's 2 of them is because the payoff phase happens twice, right? At this point, we have created 2 equivalents of GAP. We started with a 6-carbon sugar. It's been broken down into 2 equivalents of a 3-carbon molecule. Each of them have an aldehyde. The aldehyde gets oxidized to a carboxylic acid. Okay? As we already mentioned, the preparation phase invests ATP. We see here there are 2 steps that ATP gets consumed: the phosphorylation of glucose and the phosphorylation of fructose 6-phosphate. And the payoff phase happens twice. Right? This is important because there are only 2 steps that make ATP. But since the payoff phase happens twice, since we have 2 3-carbon chains, and that means we make we produce 4 ATP during the payoff phases, meaning we net gain 2 ATP molecules and 1 NADH, and 2 NADHs. Okay, let's look at these phases a little more closely. Focusing on the prep phase. Okay, step number 1 is glucose gets phosphorylated, and we're going to see that this is called the commitment step. Once this step happens, this is a highly exergonic step that commits glucose to glycolysis. Okay, that means once we've made glucose 6-phosphate, there's really no turning back. Okay, this is important for a number of reasons, which we'll talk about. One of which is when glucose comes into the cell, it can spontaneously leave the cell if the conditions are right. But once we phosphorylate it, it's trapped in the cell. It can no longer leave through the glucose channel. Okay, so step number 1 is consuming an ATP to make glucose 6-phosphate. Then glucose gets isomerized. We convert glucose 6-phosphate to fructose 6-phosphate. Okay, we are converting an aldose to a ketose. The ketose, fructose, then gets phosphorylized again. So step 1 is phosphorylating glucose. Step 2 is converting glucose to fructose. Step 3 is phosphorylating fructose. Phosphorylation, isomerization, phosphorylation. This gets us to phosphofructokinase, which is a key intermediate because fructose, unlike glucose, is not as stable in its ring form. Okay? It can very easily transition into its linear form, which is the form of the molecule that we need to undergo our reverse aldol condensation to split this into two equivalents of 3 carbon chains. Okay, we see here that fructose 1,6-bisphosphate gets split in two by this enzyme aldolase to produce a ketone, dihydroxyacetone phosphate, DHAP, and an aldehyde, glyceraldehyde 3-phosphate, GAP. These two are functionally equivalent. One's a ketone, one's an aldehyde. And just like the isomerization of converting glucose to fructose, we can readily interchange them. Okay, the enzyme that does this is called CHEM or TPI, triose phosphate isomerase. It is one of the fastest enzymes on the planet. It is limited by diffusion in and out of the active site, right? So one of the substrate, let's say the ketone DHAP, enters the active site. It's immediately converted to the aldehyde GAP, and then GAP has to leave. So the rate of the reaction is not dictated by Michaelis-Menten kinetics. Instead, it's dictated by how quickly the reactant comes in and the product diffuses out and another reactant comes in. Okay, this is our preparation phase. We end up with 2 equal equivalents of glyceraldehyde 3-phosphate. We have to be able to convert the ketone to the aldehyde because only the aldehyde moves forward. Okay, and it's important to note that ultimately we consume 2 equivalents of ATP to do this. The payoff phase. So in the payoff phase, we start with our aldehyde, glyceraldehyde 3-phosphate. In the first step, we undergo an oxidative phosphorylation. Okay, this is a term to know, oxidative phosphorylation. We oxidize carbon 1, we oxidize the aldehyde carbon, and then we phosphorylate it. Okay, the oxidation converts it to a carboxylic acid, and the phosphorylation gives us 1,3-bisphosphoglycerate. Anytime we have an oxidation, it's coupled to a reduction. So the oxidation of the aldehyde produces electrons. Those electrons are given to NAD+ to generate a reduced equivalent of NADH. That's the oxidative part of it. Phosphorylation. This is one of the places we're going to see where we're going to phosphorylate a molecule without having a phosphate donor. The source of phosphate is purely inorganic phosphate. Okay, which this is important because if ATP were consumed here, if we needed to use the energy of ATP hydrolysis, then glycolysis wouldn't net any ATP. Right? The fact that we can put this phosphate on and have this bis-phospho compound is the sole reason that glycolysis overall yields ATP. Right? Because the phosphate comes from inorganic phosphate, not from ATP. Okay? Once we've made 1,3-BPG, this is our first high energy phosphate compound. This is the first thing that's able to phosphorylate ADP. It's the first molecule we've made with a higher phosphoryl transfer potential than ATP. And whenever we make a high energy phosphate compound, the most logical thing is to use it. So the next step, we transfer a phosphate onto ADP to make ATP. We now have 3-phosphoglycerate. 3-phosphoglycerate undergoes a couple rearrangements. We move the phosphate from the 3rd carbon to the 2nd carbon. We then dehydrate it to make the enol equivalent of pyruvate. We've produced phosphoenol pyruvate. We've generated our second high energy phosphate compound. Our second high energy phosphate compound is then used. We make something with enough phosphoryl transfer potential to make ATP. we immediately use it. And that's the last step. The enzyme pyruvate kinase will then take that phosphate off of phosphoryl pyruvate and give it to ADP to make ATP. Okay, if you didn't get them all down, that's okay. The slides will be online. You have a book. But using this, make sure you can fill these things in, right? So I need you to understand all the intermediates. I need you to have a good sense for the enzymes, and writing them down over and over is the way to do that, okay? I'm going to give you some tips on how to remember these things, okay? This helps me a lot. And hopefully once we go through it, it'll help you a lot too, okay? You have two options. You have 6 carbons or 3 carbons. And honestly, the 6 carbons are easy. You have glucose or you have fructose. And hopefully you can draw glucose and fructose. Okay, if you can't, if you can draw glucose, you can draw fructose. Okay, remember, fructose is the ketose equivalent of glucose. Okay, so glucose, I can't really help you. You just kind of got to be able to draw it. The doo-doo rule, yep. And then the anomeric carbon, it can be up or down. If it's in the beta position, it's the more stable one. But at the end of the day, if you draw alpha, I don't care. Okay, so the doo-doo rule. If you want to draw it in a linear form, you can do that. But typically, we're going to draw it in the cyclic form. Okay? Glucose is going to be one of the 2 sugars you should be able to draw. Fructose is the other one. Okay, and if you remember that these 2 positions on glucose and fructose look the same, then that helps. Glucose and fructose. Okay? Phosphates are only going to go on the very ends. So we're going to have glucose 6-phosphate. Remember, the anomeric carbon is carbon 1. So this is carbon 6. So carbon 1, carbon 6. So glucose 6-phosphate. And take liberties with abbreviations. I don't need to draw out every phosphate group. Okay? That's just a waste. Unless like you have to show a reaction, save yourself time and energy. You know what this means. Glucose 6-phosphate, fructose 6-phosphate, fructose 1,6-bisphosphate. On carbon 1 or carbon 6, carbon 6 first. And that's all of the hexoses. Okay? If it helps to draw out the linear form, and it certainly will when we get to our aldolase reaction. So remember that if you can draw glucose in a linear form, that's an H. Somebody tell me, how does it go? Nobody? Right or left? On carbon 2. Okay, nobody wants to multiply. So if you can draw it out in using the doo-doo rule, remember that just rotate it. So rotate it to the right. This carbon is carbon 2. So what's down when you rotate it points right. What's up points left. What's down points right. And then this one, it's a D sugar, so it has to be right. Y'all don't remember that? We're gonna spend the next week and a half talking about sugar, so maybe you should review them. Be able to draw glucose, like for real, like be able to draw glucose, like that's the one. Okay, because you can draw glucose, you can also draw fructose. Remember, fructose is the ketose equivalent of glucose. So this is the aldose. Move the double bond here, and you have the ketose. So if this is glucose, everything else is the same. So all you really have to do is be able to remember is how to draw glucose. If you can do that, you can do the rest of them. Okay? Our 3 carbon chains. They boil down into basically 3 categories. Aldehyde, ketone, or glycerate. Okay? So all of them start with a kind of glycerol structure, like a base glycerol structure. Who remembers what glycerol is? 3 carbons, and each carbon has an alcohol group on it, right? So let's draw it like this. Glycerol. I'm good. Okay, glycerol. So all of them start with glycerol. Glycerate. Take the alcohol on carbon 1 and make it a carboxylic acid. This is glycerate. You can draw glycerol, you can draw glycerate. Glyceraldehyde. If you can draw glycerol, make carbon 1 an aldehyde. You can draw glyceraldehyde. Glycerate, glyceraldehyde, and then the only other one here is the dihydroxyacetone. This is the ketone equivalent of glycerol. So instead of making carbon 1 an aldehyde, instead of making carbon 1 a double bond, make carbon 2 double bond, and you have the ketone. Glycerate, glyceraldehyde, the ketone. Okay? For the ketone, dihydroxyacetone phosphate. It starts with here. Okay? Acetone, everybody, hopefully y'all remember acetone is a 3-carbon molecule, ketone in the middle. So dihydroxy. You have 2 alcohol groups, you have 2 places to put phosphates. Okay? So dihydroxyacetone phosphate. These carbons are equivalent, so it doesn't matter. Choose one of them and stick with it. You can name it carbon 1, carbon 2, carbon 3. It ultimately goes on to carbon 1, but it doesn't matter because they're symmetric. Okay? Dihydroxyacetone phosphate. Glyceraldehyde 3-phosphate. You can draw glyceraldehyde, put a phosphate on carbon 3, you have glyceraldehyde 3-phosphate. 1,3-bisphosphoglycerate. Glycerate, carbon 1, carbon 3, put a phosphate on carbon 3, and the only place it can go on carbon 1 is on this oxygen, right? So put it on this oxygen. 1,3-bisphosphoglycerate. Next is 3-phosphoglycerate. Okay, instead of having, so here we've gotten rid of the phosphate on carbon 1, we have 3-phosphoglycerate. 2-phosphoglycerate. If this is carbon 3 and has a phosphate and this is 3-phosphoglycerate, then carbon 2, move the phosphate, and you have 2-phosphoglycerate. Everybody following so far? I'm moving a little bit faster because we have 1 minute. All right, so honestly, I think it's easier to know how to draw pyruvate than phosphoenol pyruvate. If you can draw pyruvate, you can draw phosphoenol pyruvate. And if you can draw alanine, you can draw pyruvate. Okay? Because pyruvate is the beta keto equivalent of alanine. Okay? Alanine. Everybody can draw alanine, right? If not, I will have Dr. Hurlbert come at you. Remember, alanine is the amino acid with a single methyl group side chain. So alanine is this. Pyruvate is the beta keto equivalent of this. Okay, by that all I mean is remove the amine and replace it with a ketone. Pyruvate. not beta keto, it's an alpha keto. I wrote that wrong, and then I kept saying it wrong. The alpha keto equivalent. Okay, this is pyruvate. Phosphoenol pyruvate. Start with pyruvate, make it the enol tautomer. Okay, so if this is pyruvate, the enol tautomer looks like this. So this would be enol pyruvate. Phosphoenol pyruvate, you have the phosphate in the only place it can go, on carbon 2. Okay, so pyruvate is the ketone equivalent of alanine. Remove the amine, put a carbonyl. Phosphoenol pyruvate, start with pyruvate, convert it to the enol tautomer, and then put a phosphate on carbon 2. Okay, so there are themes to this. You just got to see it, right? Understanding the base structures and then just listening to the nomenclature will get you there. All right, this activity will not be due on Thursday, but it's currently set to be due on Thursday. But honestly, if you want to work through it, finish it up, we don't have a lot left. We're just gonna talk about some energy stuff. Okay, and then Thursday we will talk about the reactions in more detail.